In this lesson, we will talk about recursion with Python. Now, recursion is a very interesting programming technique that naturally fits certain kinds of problems. These are problems that can be subdivided into smaller problems, and the same logic could be executed on it as the original problem. Let me give an example. Searching for a file in a folder hierarchy is a very naturally recursive operation. If you're looking for a file, you would obviously look at the current folder. If you do not find it, you will go and do the same thing with each of the nested folders, which in turn might lead you to further nested folders till you finally get to the bottom of the folder hierarchy. To use recursion, we define recursive functions. These are basically functions that call themselves. So let's look at an actual example. If you recall from your math class, the operation factorial, which was defined as follows. N factorial is 1 if n is 0, or if n is greater than 0, the definition of n factorial becomes n times n minus 1 factorial. So notice that we are using factorial to define factorial. So this is a very recursive definition of an operation. So let's write this in Python code. Let's imagine we are implementing a function called factorial, and it's taking a parameter n. The job of the function is to compute n factorial. So recursive implementation, when you write it, will have two parts. There will be the stopping condition. This is the case where no recursive calls are being made, but something is simply getting returned. So in the case here, it is this case right here, where if n is 0, then you just return a value. The second part is the case where recursive call is being made, but it's being made with a smaller subproblem. So in this case, you're making a recursive call, but it is being made with a smaller problem, with n minus 1, not the original problem, which was n. For the recursive function to terminate, the subproblems must eventually be reduced to the stopping condition, to the stopping case. At the stopping case, the result is just returned to the caller, and the process continues till the result is returned to the original caller. So let's actually write this code in Python and see what it looks like. So we have the structures of our problem. We certainly have the main definition, which calls factorial and uses input for a prompt and uses int to convert it into a value. And then we're calling main just so this thing will run. The main implementation is here in this definition of the factorial function. The thing you'll notice about the body is it looks very much like the definition of the actual mathematical operation. Here is the stopping condition. If n is equal to 0, you return 1. Otherwise, you return n times factorial being called recursively on n minus 1. Very, very simple and very, very straightforward, and that is the power of recursion. If you run this thing, you will see the following. It'll prompt you for a number, and it will give you the factorial value. As we said, the definition of the function is a direct translation of the mathematical definition. The thing you will note here is the parameter is decremented every time, which is right over here. Hence, the problem space is getting smaller. And then a recursive call is made on this smaller subproblem. So if we were to actually look at how this occurs in execution, it would look like the following. Here n is 4. It would make the recursive call and return n times factorial n minus 1, in this case 3, which again would make the recursive call to factorial 2, which again would make a recursive call to factorial 1. And then you reach factorial 0, which is the stopping condition. At this point, no further recursive calls are made, and you are simply returning 1. The execution would pop back up here, and 1 times 1 would be returned up here, which is 1, and then 2 times 1 would be returned, which is 2, then 3 times 2 will be, and all the way the execution will proceed till you get to the very top level. Notice the nature of this, which is function calls made within function calls made within function calls, and so on. And when return, flow of control pops right back up. Now here's a question I have. Can we simplify the implementation of factorial to be simply like this? Actually, let's just try it out. First, we will go ahead and copy this and see what happens in PyCharm. So we have PyCharm right here. We will paste our code and get rid of a few extra lines and run it. So if we enter 7, you would get back some value. Now, the question I have asked is, what happens if I simplify it, right? So here I'm removing the condition, because ultimately I'll get to 0. So here I'm removing the condition of the stopping condition. Now you can probably imagine what will happen is that there's no way for this program to stop. So you'll keep on decrementing n over and over again. You'll go into negative territory and there will be no stopping this. So let's actually try that out and see what it looks like in code when something like this, when something like this happens. So here, let's enter 7 again, and you will see what has happened. It kept on calling it over and over again. It did it about 995 times, and then it gave up. And it said it's a recursion error, maximum recursion depth reached. So it does have a check. Python does have a check for that, right? So that's exactly what I'm showing here. This condition is called infinite recursion. So let's actually see what is happening when functions are being called within function. Every time a function is called, the programming environment, the programming system, allocates a record in memory. And the memory goes like a stack, one on top of another. So when factorial 4 is called, there is an activation record allocated. Local values like n are stored in there to be able to be recovered later on. When factorial 3 is called recursively, another activation record is added. The first one is preserved because you would need to return to it when you're done with the recursive call. And on it goes, and you keep on adding it till you reach 0. At this point, factorial 0 will return, and you will start popping the activation record till you reach the following one. If you have infinite recursion, this activation record will keep on growing and may eat up all the memory, and that's why Python stops you after a while, saying something is going wrong. Now let's take a look at another recursion example. This time we'll look at a series called Fibonacci. It's a well-known math series. Leonardo Fibonacci was a medieval mathematician that originally used it to model growth of rabbit population. So Fibonacci of a particular index is defined as follows. If the index is 0, the value of Fibonacci is 0. If the index is 1, the value of Fibonacci is 1. If index is greater than 1, then the value of Fibonacci is basically the sum of the last two numbers in the series. The series looks like this. The first two, as we said, is 0 and 1. After that, it is the sum of the last two in the series. So this one is the sum of these two. This one is the sum of these two. This one is the sum of these two, and so on it goes. Note the stopping condition here is here, and the recursive calls are here. The difference here is that there are two recursive calls. And for each recursive call, the index is reduced, so the problem space has gotten smaller. So what does this look like in code? Again, the code is very simple. This is our main implementation of Fibonacci. We're calling it fib. We have the two stopping condition, and we have now two recursive calls. If you run it, we'll give you the value back. We can actually try this out. Let's copy this. Start off PyCharm. We'll get rid of our previous stuff here, and then we'll just paste this here. And let's run it. And if we say 7, it'll give you back the Fibonacci value. If you go back to our series, you will see 0, 1, 2, 3, 4, 5, 6, 7, and that's why you're getting the 13 that we just did. Now let's look at the recursive call hierarchy for calling Fibonacci, just like we did previously for factorial. If you call Fibonacci fib4, you are making two recursive calls now. The one on the right-hand side would make further recursive calls to fib1 and fib0, and then ultimately values will be returned back. The one on the left would make its own recursive calls and back. Now there's a problem here. You will notice that there are quite a few duplicated recursive calls. For example, Fibonacci 2 is called twice, here and here. Fibonacci 1 is called 3 times, here, here, and here. In fact, we can instrument our code to see how many recursive calls are being made. So we have the same program as above. The parts in color are the ones we have added. What we've done is defined a global variable, a variable that has scope through the whole program to hold the number of times Fibonacci is called, the fib function is called. Every time fib is called, we increment it by 1. Notice the declaration global followed by the variable name. This indicates to Python that CNT is a global variable. And at the end, we print out the number of recursive calls. So let's actually try this out. We're going to copy this, and we're going to replace our earlier program with this. So let's try this out. Suppose we just said our fib4. It shows that the number of recursive calls there are 9 recursive calls that are being made. And let's keep trying this. We'll make this a little bigger so we can see it more easily. And let's do 10. Now there's 177. Let's do 15. And now it's 1,973, so it's growing quite fast. Let's try 20. Okay, 21,000, almost 22,000. Let's try 30. Wow, so this is more than 2 million, 2.7 million. And let's try 40. Wow, it's doing so many that we are having to wait a little bit, and ultimately, hopefully, it will return. Well, it's still going on. So something interesting is happening. So actually, I have an output of running this here, and that's exactly what we showed. When you enter 40, you get ready to wait a little bit, and then ultimately it will return the value. And this is 311 million recursive calls that are being made. So recursive implementations can be very inefficient if you are not careful. And later on, we'll talk about how to improve that in lesson on loops. Loops are a lot more efficient than recursion, but certain things are naturally recursive, and it's a lot easier to code them using recursive functions. So let's talk about recursion in general. In popular culture, we have seen recursion. You will notice this picture, and it'll remind you of the movie Inception, where people are dreaming within dreams. In fact, there was an image in 1904 for a Dutch Coca brand, which used recursion. You'll notice the model here is holding a tray with a box, which shows the same picture as this, which is, so it's recursively the same picture is being shown over and over again. This actually is called the Dorste effect, and it's used in all sorts of situations, such as here, where a person is looking at a picture which shows the same scene with them in it. You can actually do a Google image search for this and shows you all sorts of interesting examples. So talking about recursion in general, recursive functions have the following characteristics. They typically use if-else or some kind of conditional statements where you have different cases. There are one or more stopping conditions, as we've seen, and then there are recursive calls, but the recursive calls reduce the original problem to a smaller problem. that ultimately leads back to the stopping condition. Right? So to solve problems, recursive problems, you have to be able to break them down into sub-problems, which are the same as the original problem, but smaller in size. In fact, there's programming languages that are defined around recursion, and one of them is this one called Lisp that is fundamentally based on recursion. So this has been a lesson on recursion.